Welcome, everybody. Today's lecture will be on equations with linear coefficients. And by an equation with a linear coefficient, I mean an equation which can be written in the form I have down here. So you can see the coefficients of both dx and dy are linear combinations of x and y. So the a's, b's, and c's are all real numbers. And so notice, this is actually before case one, you can just rewrite that sometimes when it's convenient as y prime is this rational function, okay? So there'll be three cases to consider. Two will reduce to things we already know how to solve, and one will need to think of a genuinely new method, okay? So case one is going to be when b1 is equal to a2, okay? And actually, we don't need equation two for that. Let me rewrite one, and instead of b1, I'll put in a2. And I'll call that coefficient of dx m and that coefficient of dy n. So I can bet you can guess where this is leading. So if I take the partial of m with respect to y, I get a2. And if I take the partial of n with respect to x, I get a2. So this equation is exact, and we can solve it by the methods we learned already. So we won't talk about that any more about that because you already know how to do that. Okay. So in case two, we want to consider where A1, B2 is A2, B1. Okay. And so in that case, I take that equation two, which remember looked like that was this one. So where you write it as a ratio. And I'm just interested in what this right-hand side is. So I don't really need to worry about the minus sign. And I want to know, when is it possible to write that ratio as a function of just a linear function with a single coefficient of a, like for example, in the form ax plus by. But to make this clear, I'm going to do a little trick and multiplying the numerator and denominator by x, or so 1 over x really. So that that multiplying by 1, I haven't changed anything. So notice that I can write this ratio in this form. And I want to know, when can I write that? Looks a little cleaner to do it this way, as a plus b times y over x. Okay, so in other words, let's take this equation and multiply through by the denominator. So I get a2x, a2, sorry, this equation. So that gives me a2 plus b2y over x times a plus by over x. And that's going to be equal to a1by over x. All right, so let's multiply that out. When you multiply that out, you'll have a2 capital A plus ab2y over x plus a2by over x plus bb2y squared over x squared, and that's going to be equal to a1 plus b1y over x. Okay, well, that's two polynomials. If they're equal, the coefficients have to be equal. So that says that the constant term, which is a2a on the left, has to be equal to the constant term on the right, which is a1. The coefficient of y over x on the left, which is a2b2, ab2 plus a2b, has to be equal to the coefficient of y over x on the right, so that's b1. And the coefficient of the squared term, which is b1b, has to be 0 because there's no squared term on this side. Okay, so what does that say? Let's start figuring that out. So that says b2b equals 0, but b2 is part of our given equation. It's not necessarily 0, so that implies that b has to be 0. Okay, so if b has to be 0, b equals 0, says from this equation that a2b has to be equal to b1. This equation says a times a2, a has to be equal to a1 over a2. So a1 over a2 times b2 has to be equal to b1, and that says a1 b2 has to be equal to b2 b1 a2. Okay, so which is what we assumed. So if this is true, and all of these are if and only if, so we can go backwards. If this is true, then I can write the right-hand side of my equation 2 as a single function of a plus b y over b times y over x. So 2 becomes y prime is a plus b y over x. Okay. So notice that this is actually in the form y prime minus b over xy is equal to a, which is a linear equation. And so we know how to solve it. Okay. All right, so we are done with case 2. So in the case where A2, A1, B2 is A2, B1, it reduces to a linear equation. All right, so now I did this calculation. Notice I did this calculation in the case C1 equals C2 equals 0, but you can do a similar thing if C1 and C2 are not 0. Okay, I'll leave that to you to play around with. All right, so now I'll also do case 3 in the case where C1 and C2 is 0. So case 3, A1, B2 is not equal to A2, B1, but we do in the case C1 equals C2 equals 0, at least to start. And I'll say how you can handle that later on, okay? Okay, so then our equation that we started with, because of that assumption, looks like a1x plus b1y plus a2x plus b2y dy dx equals 0. Okay. All right. So as we noticed before, you can write that as dy over dx is minus a1x plus b1y over a2x plus b2y, and now multiplying by 1 over x in the numerator and denominator, that is a1 plus b1y over x, and a2 plus b2y over x. Okay. All right. And now you stare at that for a second, and you see that this right-hand side only depends on the ratio y over x. So it's so that gives us a homogeneous equation. And so we can solve it by the method we discussed a couple of submodules ago. Okay. All right. So now what do you do? What if C1 and C2 are not 0? Okay. All right. So what are we going to do? What we're going to, and we're in the case A1, B2 is not equal to A2, B1. Okay. So what we're going to do is we're going to introduce, we're basically going to shift the axes. We're going to let x be equal to u plus h and y be equal to v plus k. And h and k are constants. Okay, and we want to find what h and k are constants and chosen so that a1x plus b1y plus c1 equals a1u plus b1v, and a2x plus b2y plus c2 is equal to a2u plus b2v. Okay. All right, so we're going to try to shift things so that we can get an equation that we know how to solve from this case for u and v. And then once we do that, if we know v and we can figure out h and k from C1 and C2, then we ought to be able to go back and find our x and x and y. Okay, so let's see what that says. What does that say? All right, it says that now I'm going to put in u plus h for x and v plus k for y. So let me call this one, I had a 1 and a 2. Let me call this 3 and this 4. Okay, so I'm going to put in u plus h and v plus k in 3. We get a1 u plus h plus b1 v plus k plus c1 is equal to a1u plus b1v. Okay, so let's see, what does that tell me? That says a1u plus a1h plus b1v plus b1k plus c1 equals a1u plus b1v. Okay, so a1u, a1u, b1v, b1v. All right, so that tells me that for 3 to be true, it's sufficient to say that a1h plus b1k is equal to minus c1. Okay. All right, now what about 4? Well, you see a similar calculation for 4 is going to give me that a2 u plus h plus b2 v plus k plus c2 has to be equal to, not 0, sorry, it has to be equal to a2u plus a2 plus b2v. And the same sort of expansion will easily show you that a2h, that 4 holds if and only if a2h plus b2k is equal to minus c2. Okay. So in other words, you know your A1, you know your B2, you know your C1, and you know your C2. I'm leaving out some of those, but you know all the AIs, the BIs, and the CIs. So you have 2 equations in 2 unknowns for the H and K. So this is 2 equations, 2 unknowns. So you can solve by linear algebra. When can you solve that actually explicitly? Well, if you haven't had linear algebra before, you're at a tiny bit of a disadvantage. But if you have had it before, and you just have to believe me, if you have had it before, you know that you can solve this system of equations. I'm sorry, this should be a B1K. That was equation 3, or what's equivalent to equation 3, and what's equivalent to equation 4. This is a B2K is minus C2. You can solve for H and K if and only if the determinant of the coefficient matrix of H and K is non-zero, which says that A1B2 is not equal to A2B1. Okay, I'm not going to go into the linear algebra. If you've had it before, you write it as the matrix system A1, B1, A2, B2 times HK is equal to minus C1, C2. So you think of it, this is A times your unknown matrix equals a given constant matrix. When can you solve that? When A is invertible. When is A invertible? When the determinant of this matrix is non-zero. That's exactly that statement. Okay, so we can find an H and K to satisfy, we can find an H and K so that we can change the the numerator and denominator in our rational function in equation 2 to the linear function with zero as the with zero with C1 with no constant term in it in terms of u and v. Okay, so so let's move this here. Okay, so that means that our original equation, which remember, it's been a few sheets since we've seen that, it said dy dx is minus a1, let's put the minus sign out in front, minus a1x plus b1y plus c1 over a2x plus b2y plus c2. Okay, and remember that x is u plus h and y is v plus k, and h and k are constants. So notice that dy dx is going to be the same as du, and dy is the same as dv. So dy over dx is the same thing as dv over du. This right-hand side, by the calculation we just did, can be written as a1u plus a2a plus b1v. Okay, divided by a2u plus b2v. Okay, and now we use the same trick that we did before. We'll multiply in the numerator and denominator by 1 over u. So dv over du will be equal to a plus bv over u plus a2, that's a b1, plus b2v over u. Okay, and then this is a homogeneous equation. So we can solve by our previous methods. Okay. All right, so let's try an example. Okay, let's look at, I don't know, let's say 2x minus y plus 4 dx plus x minus 2y minus 2 dy equals 0. Okay, so this one is one where we have a constant in both terms. Notice this is a constant times x, constant times y, plus a c1, and you have a c2 in this term as well. Okay, and so now we want to check. Now b1, so a1 is 2, b1 is minus 1, c1 is 4, a2 is 1, b2 is minus 2, and c2 is minus 2. So if we look at a1 b2 minus b2 a1, that's not 0 because you get minus 4 plus 1, that's not 0. So we're in that third case. All right, so we want to try to shift the axes. So in other words, let me remind you that a1 b2 does not equal a2 b1. Okay. All right, so we want to set things so that x is equal to u plus h and y is equal to v plus k. And we want our equations to satisfy the system that we derived before, which actually I have written up here. So the system is that a1h plus b1k is minus c1, and a2h plus b2k is minus c2. So here, that gives me the equations 2h minus k is equal to minus 4, and h minus 2k is equal to 2. Okay, solve it by your favorite method. If you know linear algebra, you can do it that way. You don't need all that stuff. This is an easy equation to solve by regular algebra. I'm going to just solve it by substitution. So the second line says that h is 2 plus 2k. I'll put in that for h up here. So 2 times 2 plus 2k minus k is minus 4. So that's 4 plus 4k minus k. So that's 4 plus 3k is minus 4. That says 3k is minus 8. So k is minus 8 over 3. Okay. Whoops, sorry, off the paper. And so if k is minus 8 over 3, then this is 2 minus 16 over 3. So that's 6 over 3 minus 16 over 3. That h is minus 10 over 3. Okay. Okay. So now we go back to our equation. Okay. We go back to our equation. We're going to need some more room here. So let's see, maybe like this. Okay. All right. And let's see, we go back to our equation. There's our h and our k. And so we get that our equation is dv over du is equal to a1u. Let's see, our a1 was, so it becomes 2u minus b divided by u minus 2v. It's the same coefficients you had up here, but with the constants gone now. We've chosen things so that the constants go away. And now we're just solving a homogeneous equation, and we'll use h and k again, their values at the end. So I write this as 2 minus v over u, 1 minus 2v over u, okay? And now I need to use the method to solve homogeneous equations. So I'm a little bit running out of letters here, but what's a good letter? Maybe W. Let's let W be V over U. And remember, we're thinking of V as the independent one, U is the dependent one. So WU equals V. So dV du, using this and the product rule, is going to say dW du times U plus W. Okay. And so we replace dV du by that. So it's dW over du times U plus W is equal to 2 minus W divided by 1 minus 2W. Okay. Okay, so now we want to solve this. So let's do a little moving things around. So I have 2 minus W over 1 minus 2W. And then I need to subtract W. So let's get a common denominator. So I have 2 minus W. And then I will have a minus W and a plus 2W squared. Okay. So when we rewrite this the next time, we'll notice that this is 2 minus 2W plus 2. Well, let's go ahead and do that. So we'll notice that is 2 times 1 minus W plus W squared divided by 1 minus 2W is dW times U over du. Okay. And now let's rearrange things because that's a separable equation. So we get 1 minus 2W over 1 minus W plus W squared is equal to 2 over U du. Okay, doing the algebra, which I think it was done carefully. So it's separated because all the U stuff is on the right and all the W stuff is on the left. So we can integrate. On this side, it's easy. You have just 2 ln absolute value of U. Over here, we do a quick little substitution. let's let S, yeah, we haven't used S. So let's S be W squared minus W plus 1. Then ds is 2W minus 1 times dw. Okay, so what you have on the right-hand side is minus ds over s. Over here, you get 2 ln absolute value of u plus c. On this side, this integrates to minus ln absolute value of s. But s was w squared minus w plus 1. Okay. And that's equal to 2 ln u plus c. Okay. And so w was v over u. So this is minus ln let's see, w was v squared over u squared minus v over u plus 1 is equal to 2 ln u. Okay. Maybe it would be best to get this as a single rational function. So I'm going to write this as ln of u squared, and then my numerator here is v squared. This one will be v times u, and this will be plus u squared is equal to ln absolute value of u plus c, 2 ln absolute value of u plus c. Let's bring this to the other side, and I can change my constant c, and then I will have, now notice ln, 2 ln u is ln of u squared. Then you don't need the absolute value signs. And when this comes to the other side, it's a plus. Okay. When you're adding the log of two numbers, that means you're multiplying the numbers. So this is ln of u squared times what's inside. So that just gives me a v squared minus v times u plus u squared in absolute value. Okay. All right. Okay, so let's move to another sheet of paper. So we have C is ln of v squared minus vu plus u squared. Okay. All right, now let's see. We had before that, so u plus h is x and v plus k is y, and k is minus 8 over 3 and h is minus 10 over 3. Okay. All right, so there are a couple of ways I could do this. Well, it's sort of 6 of one, half dozen of another. Okay, so let's just go ahead and write it out. We'll use brute force. Never kills you. Okay, so V is y plus y minus k, and k was minus 8 over 3. So this is y plus 8 over 3, quantity squared, minus y plus 8 over 3 times u, which is u is x minus h, and h was minus 10 over 3. So that's x plus 10 over 3 plus x plus 10 over 3 quantity squared in absolute value equals c. Okay. All right. And so you can play around with that a little, but you're not going to get it to be a whole bunch prettier than that. And you will not be able to get an explicit form for the solution. So anyway, there's an example of how you can see the equation, an equation with linear coefficients. solved in sort of the messiest of the cases. Okay, that's it for today's lecture. Hope that helps. Bye.